Good afternoon, everybody. This is the routing session, session 3A. Hopefully you're all here for that. We're now a couple minutes past, so hopefully we have everybody managing to wander in. So we'll go ahead and get started here. The first paper in this session, we have Proof of Backhaul, Trustfree Measurement of Broadband Bandwidth by Peiyou Shang. So I'd like to welcome her up here to walk us through her presentation.
Okay, thanks everyone for being here. My name is Peiyou. I'm a PhD student at the University of Illinois, Urbana-Champaign. This is a joint work conducted at Witness Chain with my colleagues Nikita, Visha, Aram, Anand, Himanshu, and Pramod. So the idea of open networking is an old dream, as old as the internet itself. Since 1990s, the network has been designed to be distributed and decentralized. It was built out of heterogeneous network components, and the underlying protocols such as TCP/IP and DNS are all meant to be decentralized. This is the age of Web 1.0. But today, decades later, everything seems to be taken over by the giants. Most of them are platform companies such as Apple, Amazon, and they control the dominating content delivery network from data centers to cloud computing. So in the world of Web 2.0, everything has become more significantly more centralized. However, the tailwinds of decentralization is blowing again for networking. Spectrum is being opened up. We have slightly licensed airwaves such as CBRS, and companies like Google has demonstrated ability to manage this shared spectrum over different tiers of users. And there is elastic computing platform, so the network core can be entirely moved to the cloud because of the accessible and affordable computing resources. And we have more lightweight hardware. We can buy the Wi-Fi access points or cellular base stations for our own. And additionally, those decentralized base stations, such as healing hotspots, are emerging in a token-driven ecosystem. So the convergence of all this business, engineering, and policy development, we have the decentralization of network as enabled by all these components. Now the key challenge is how can we stitch these different components together in a low-friction way and also incentivize different participants to behave properly. Low friction here means open and trustless. In other words, we don't want to ask everyone to sit down with some lawyer to negotiate before participation. And with this trust, we also want to utilize tokenization for providing incentives. So these two desired properties naturally bring blockchains into the story. And on top of that, we need a new class of protocols to support these different environments. So what do these kind of protocols look like? One particular example, which our paper focuses on, is the network telemetry problem, which is an important and on its own a mature problem. So because people all are interested in measuring the network performance, and they will utilize the results to further optimize the network performance by, for example, monitoring the potential attacks or identifying bottleneck link over the internet. So these are all traditional usage of the network telemetry. When it comes to the decentralized setting, these traditional use cases still apply, but we also need to consider extra constraints. How can we make it open and trust-free, which means there's no powerful service and no trusted party we can utilize? And how can we get network meritocracy and make use of it to drive the system performance? Our solution to this problem is a proof system that establishes how much each party can contribute to the backhaul bandwidth, and we refer to it as proof of backhaul. And here's a diagram depicts the main components of the system. Particularly, there's a hotbot, we call it a prover, who want to make the claim that it has a good backhaul connection to the internet. And on the other side, there are different servers who can issue challenge traffic to the hotbot to make sure, to check whether the claim by the hotbot is correct or not. And such setting is not a new problem. We've seen many centralized measurement techniques, such as speed test, will give us a very straightforward dashboard like this. And what essentially speed test does is that they maintain a pool of servers, and when there is a challenge, they will pick one of the most closest server to the service provider, and then ask the server. And the server should have high bandwidth, low latency, and low packet loss. And it will ask the server to generate a dedicated foreground traffic to flood the connection. And this kind of method is obviously not open because it has high barrier to entry. Those small servers whose bandwidth is less than the bottleneck link cannot become the challenge server. And also, the method is not trust-free. We have to trust the challenge server for providing the data and the prover to measure the time. So one technique you want to utilize to remove the requirements of those powerful server is traffic aggregation. Now, instead of a single server, we ask a group of challengers to generate the packets in parallel. And these packets are later transmitted through the internet and aggregated before the measured link. So they're equivalently heavier form of heavier flow. This kind of technique has also been used in some work, including the speed test itself, to improve the accuracy of the measurements. But the method does not provide any robustness for tolerating the malicious prover or any collusions among parties. So to eliminate the trust on the prover or any single party, we have to find a way to interact. Because if we just wait for the prover to report their performance, they can, of course, say whatever they want. But if we gather information from multiple parties, then they can help to verify what is claimed by the prover. Basic interactive measurement tools, such as Pascal, has utilized the timing information from ICMP packets to estimate the round-trip time. And particularly, for a given target link, the protocol will generate 2 different flows to measure the RTT from the source node to 2 different end nodes, and then calculate the difference to output the bandwidth. This kind of method introduced the measurements from another party. Here is the intermediate nodes. And in our setting, it's the ISP itself, which is assumed to be trusted in the problem. So now the prover cannot manipulate the measurement, and it also, in other words, we offload the trust from the prover. But it's still well known that such method doesn't perform well when measuring high bandwidth provers because of the network jitter. So there's still a problem that we need to make it open to those provers without high bandwidth. So how about combining these 2 techniques? The aggregation will make the system a bit more open, and we have interactivity to collect timing signals as the feedback. Even so, there are more attacks we need to consider. For example, the challengers can refuse to send the packets, which is called withholding attack. And the prover can collude with some challengers to, for example, send packets through some faster external channel. In this way, they can inflate the bandwidth. We call it rushing attacks. So we need to address all these attacks in the proposed solution, and our main result is an interactive measurement scheme which provides Byzantine fault tolerance. And the tolerance level is naturally captured by the fraction of Byzantine parties, and there is an explicit bond of 1/2. Then the protocol will provide the following security properties. First, it will guarantee soundness, that is, no prover can inflate the bandwidth. This is a good one. But then the adversary can try to mess things up by bring down the performance of honest provers. So we need the second property called approximate completeness, which ensures if the prover is honest, then the protocol will output the bandwidth with an accuracy guarantee. And accuracy is expressed in this term alpha, where n is the number of challengers and f is the number of Byzantine parties. Then to achieve these properties, we're going to look at how the protocol works. We first introduce several primitives the protocol will use. Firstly is the unforgeable packets, where we ask the challengers to generate the traffic by signing some common messages. So we are going to use digital signature infrastructure. And also because we cannot trust the measurement from a single party, so we are going to implement a robust timing measurement by taking the median of the reports, which is ensured to bounded by honest reports. And the third one is we utilize the hash and Merkle tree to generate some short response to indicate the end of the protocol, so that we can minimize the return trip time and make it negligible when computing the bandwidth. Then let's go over the workflow of the protocol. So before that, here we've seen besides the challengers and provers we've just introduced, there is another important role called verifier in the system. Here, the responsibility of verifier is to take the inputs of some parties and then broadcast it to the other parties. And since all the messages are verifiable, so the verifier is essentially a trusted broadcast channel. And in our setting, blockchain is a good fit, but it can be as general as some other implementations. And then the protocol starts with a measurement phase, where all the challengers sign a common message with their secret key to generate the sequence of packets. And these packets are later transmitted through the internet and aggregated before the backhaul link we want to measure. And upon receiving enough packets, the prover immediately generates a short response consisting of the root of some Merkle tree generated from those packets, and also the hash of individual nodes to different corresponding challengers. And the packet received will also be uploaded to the blockchain. Then this response is received by the challenger, and the challengers will locally verify whether enough packets has been received by the prover. And then they will report the round-trip time to the verifier, who will later conduct the computation of the final output. So summarizing the whole process, there are essentially four steps and 2 phases. The first 2 are the measurement phase, where traffic is aggregated, and then the prover will calculate the receipts. And the last 2 steps are the verification phase, where challengers will conduct the verification, and then the RTT is robustly gathered by the verifier. So on top of the main protocol we've just presented, we also explore the design scope of the problem by changing the availability of different kinds of resources. Specifically, we have derived 3 different variants of the protocol by first replacing the UDP packets with TCP packets. So it will provide extra properties like fairness. And the second, we try to remove the utilization of signature, and we replace it with pseudo-random generator. And the third one is we relax the threat model so that adversary has no access to the extra link. So all these different variants have provided us different security theoretical bounds on the accuracy, which are summarized in this table. And such exploration also shows the protocol has adaptability and the flexibility in terms of different application and requirements of the environments. And lastly, we have implemented a protocol to test its practicality. Because besides the theoretical model, there are more factors we need to consider, such as network jitter, synchronization error, and those computational overhead for hashes or signatures. After thinking of all these factors, we implement this protocol in a lightweight way, so in terms of the amount of challenge data. And we also make sure it's open because the challenges are geographically spread and they may only have low bandwidth. And we simulate those rushing and withholding attack to make sure it's secure not only under theoretical analysis and also evaluated by the experiments. So in summary, the trust-free telemetry is a central problem in the decentralized network. And our paper tried to address one key aspect of the telemetry problem that provides the accurate and secure measurements for broadband bandwidth. And there are also other parts or aspects of the proof system, which is an interesting and broader future work. So I will stop there, and I'm happy to take any questions.
Yeah, let's thank the speaker. Any questions? Yeah, please state your name and affiliation.
Okay, hi. Thank you. I'm Rasberg from Yukon. So I'm just curious, so in the response, if I understood correctly, you're using a Merkle tree of the different queries, right?
Yeah.
So you need to wait for all the queries to arrive in order to compute it, won't you?
Yeah, so we need to wait for all the packets or enough packets to be received before computing the response.
So that means that the prover can actually play a bit with the time, because if the responses are not arrived at the same time.
Yeah, but in that case, because those packets are unforgeable, so the prover can only inflate the time of receiving if the prover is malicious, yeah.
Can only inflate the time. I mean, if the packets are received at different times, so the packets which were received long ago, you can claim to have received now. Packets you received now, you can claim to have received earlier, right? I mean, right? I mean, you cannot. Basically, you only give a single secure timestamp for all of them, right?
Yeah. So yeah, the prover will send back the response at the same time to all the challengers. So the RTT they are measuring are actually the same timestamp, but yeah, given
the RTT will be different, right? Because each of them have been sending at a different time, slightly, right? And the responses are all sent together. So if the prover received the queries at different times, then you have this gap in time. And the motivation for that was just to make the response shorter, but you still have to send it to each of the challengers individually, right? Because it's not a broadcast network. I'm not sure what do you save here. I mean, you see the loss is pretty clear, and I'm a bit at a loss at what are you really saving, because you would have to send to each of them, correct? So what is the motivation for this design?
Just to make sure I understand questions, are you referring to the case where the prover may send back response at different times to manipulate?
No. He's sending responses, like you said, to everybody together because he's using the Merkle tree. So he has this one timestamp, which is the time at which it sent all the responses together.
Yeah.
But some responses, some of the challenges it received earlier, some later. So it's giving only one timestamp. So you're losing some accuracy here for all of the timestamps.
Yeah. So
right. And but then you still.
I'm guessing we should take this question offline.
Sure. Okay. Thank you. Bye.
Yeah.
Yeah. Thank you.